Hello friends, today we are going to discuss one of the important topic about glycogenesis and glycogenolysis, which comes under the head glycogen metabolism. Glycogen metabolism. Glycogenesis and glycogenolysis. Genolysis. The name it implied, glycogenesis, synthesis of glycogen from glucose. Synthesis of glycogen from glucose. From glucose. Whereas glycogenolysis is the reverse. Degradation of glycogen to glucose. To glucose. Okay. We'll discuss one by one. Okay. What is glycogen? Glycogen is the stored form of glucose in animals, just like the starch in plants. It is stored in liver and muscle in the way of granules in the cytosol, where both the glycogenesis and glycogenolysis takes place. Why only in the cytosol? Because it contains most of the enzymes responsible for the glycogenesis and glycogenolysis. Regarding the basics, glycogenesis, it takes place. That means what we call stored form of glucose. Okay, regarding this basics, I'm discussing about liver and muscle are the major sources of storage in cytosol in the way of granules. And next most interesting question, why glycogen is the fuel reserve? Why not others? There are certain factors that makes glycogen as a potential component as a fuel reserve. Say, glycogen can be rapidly mobilized. Number two, glycogen can generate energy even in the absence of oxygen, unlike fats that cannot be. And at the same time, it is not that easy to move, that means to mobilize fats rapidly. And most importantly, brain require continuous supply of glucose. Through glycogen only we can get a continuous supply, what we call sustainable supply of glucose to brain is coming from glycogen because of these three parameters. That means, say, rapid mobility, then even in the absence of oxygen also generate energy, and for brain parameters, for brain continuous supply of glucose. Okay. Regarding its structural aspects, it's all about basics. Starch in case of plants exists in two forms. Starch, it is nothing but a homopolymer of glucose. It exists in two forms, say amylose and amylopectin. Amylose is a linear polymer held together by alpha 1,4 glycosidic bonds, whereas amylopectin is a branch, just like tree, held together. That means the branch points are held together by alpha 1,6 glycosidic bonds. Here, glycogen appears, that means similar to that of amylopectin, but much extensive branching. That means similar to amylopectin, but more number of branches are there. Okay, and this is about the structural issues. The glycogen metabolism is one of the important fragment of carbohydrate metabolisms. We have discussed in a previous class about glycolysis, Krebs cycle. These are all one of the domain, that means different domains of carbohydrate metabolisms. Apart from these two, they also have gluconeogenesis, hexose monophosphate shunt, galactose metabolism, etc. So there are different carbohydrate metabolisms under which glycogen metabolism is important fragment. Okay, it's about the basics about glycogen. Then we have to discuss about, before we go into the exact topic, that means glycogenesis and genolysis, we have to understand the basic structure of a glycogen for better understanding. Okay, as I said, glycogen is nothing but a homopolymer and is similar to that of amylopectin. That means much extensive tree branch-like structures are present in glycogen. So this is the glucose, the basic structure of glucose I'm writing. Alpha D glucopyranose, what we call. Is alpha D glucopyranose. Okay, this is the basic structure of glucose. Respect to why I have drawn this, because glucose is a fundamental block or elementary component of glycogen. Say, as I said, glycogen consists of two important bonding pattern. One alpha 1,4 glycosidic bonds and two alpha 1,6 glycosidic bonds. It's nothing about, it's simple. Glucose are the repeating units. They held together by alpha 1,4 glycosidic bonds in a linear arrangement, whereas alpha 1,6 glycosidic bond at the branches. That's it. You know, I'll draw how. Say, for example, say this is one glucose. Is one component and this is another one. You know, I told you, linear polymer held together by alpha 1,4 glycosidic bond. This is alpha 1,4 glycosidic bond. Glycosidic bond. See what exactly it means. This is one glucose unit and this is another one. The first carbon of here, the first glucose and the subsequent glucose, the fourth carbon, will involve in bonding pattern called alpha 1,4 glycosidic bond. It is with respect to a linear chain, okay, and it will continues likewise. That means n times. That means linear fashion. It will continue. It will keep on moving. Okay, with respect to branched thing, this is also important. You know, say the same compound. That means alpha 1,6 here. Alpha 1,6 glycosidic bonds. Just only a small adjustment, you know. For example, this is the first carbon. Right away here. The sixth carbon will be involved in the bonding pattern. That's same component, you know. Okay. That means here the first carbon, this is alpha 1,6 glycosidic bond and this is alpha 1,4 glycosidic bonds. Here this is called branching point. This is a branching point. And again it will repeats. Likewise, you know, the same, the alpha 1,4 with respect to, you know, linear fashion, and the alpha 1,6, that means alpha 1,6 glycosidic bonds with respect to, is a branched point. It's about the basic structure of, that means, different bonds involved in a glycogen. Alpha 1,6, this is very important, and alpha 1,4 and alpha 1,6 glycosidic bonds. Then, with respect to glycogenesis, before we go into discussion, the point is very simple. With respect to glycogenesis means synthesis of glycogen from glucose. How? Simply by adding the glucose units in both alpha 1,4 in case of linear and in case of branches alpha 1,6. That's it. This is about glycogenesis. But as about glycogenolysis, simply it means the breaking down of these two bonds. That means alpha 1,4 and alpha 1,6 in a sequential fashion. That's it. So understanding the bonding pattern is most important before going to the discussion. Okay. Then coming to the discussion of glycogenesis, I already explained that glycogenesis will take place in liver and muscle. It's a sequential reaction. The sequential reaction which involve main important events like first, synthesis of UDP glucose. Number 2, production of glycogen primer. Number 3, glycogen synthesis in a linear arrangement by means of, that means by catalyzing by the enzyme glycogen synthase. Number 4, branching pattern by glycosyl 1,4,6 transferase. That means these are the different steps involving in glycogen synthesis. That means glycogenesis. For example, in simplification, UDP glucose synthesis. Number 2, glycogen primer. Number 3, synthesis of glycogen. In the sense, glycogen synthase. Number 4, branching pattern. That means branching synthesis by means of glucosyl alpha 4,6 transferase. Glucose, the first UDP glucose synthesis, then the glycogen primer. So the enzyme is glycogen initiator synthase. Initiator synthase. Here the enzyme is glycogen synthase. Here the enzyme is, that means for regarding branching, elongation, but it is called synthesis of glycogen. That means elongation, then branching formation. This is by means of glucosyl alpha 4,6 transferase. I will tell you how it works. Okay. Say the first most important point is, say we get the glucose will be subjected to an enzymatic action that converts into glucose 6-phosphate by means of an enzyme glucokinase. Here one ATP will be utilized. Then after that means that after we get the glucose 6-phosphate, it will undergo the next reaction that leads to production, that leads to glucose 1-phosphate synthesis. 1-phosphate by phosphoglucomutase. And this synthesis of glucose 1-phosphate is very important because it is a one that becomes UDP glucose. And UDP glucose is very important because it is a form which is accepted during glycogen synthesis, that means extension. So for UDP glucose 1-phosphate is essential. And for how it forms, simply by means of catalyzing by the enzyme activity, glucose phosphoglucomutase converts glucose 6-phosphate to glucose 1-phosphate, and this glucose 1-phosphate become UDP glucose. UDP glucose means uridine diphosphate. Uridine diphosphate glucose. You know how? Here, say the UTP is pyrophosphate. That catalyzing enzyme is UDP glucose pyrophosphorylase. UDP glucose pyrophosphorylase, which synthesize UDP glucose. This is a very important step. The first step, UDP glucose is done, and this UDP glucose enters into, that means it involved in the generation of glycogen primer. What is glycogen primer? It is the initiator component, just like in DNA replication. The same, the glycogen primer is essential for the synthesis, for the extent, for elongation of the glycogen chain, and also for branching pattern. And what exactly is glycogen primer? In general, it is said that a small fragment of the pre-existing glycogen will serve as glycogen primer. But no, a new protein called glycogenin. Glycogenin, glycogenin. This plays an important role in the glycogen synthesis, means initiation. How? And this glycogenin will accept. How means? Say it contains, this is glycogenin. For example, this is glycogenin. It's a polypeptide. The tyrosine residue, which contains hydroxyl group. That means the hydroxyl group of tyrosine residue of glycogenin will accept the UDP glucose. How it ends? It leads to UDP. UDP, then the glucose. Say the point is simple. This is the hydroxyl group, and we used to add the UDP glucose here. UDP glucose. Then we'll act on this. Then we'll get here. That means UDP glucose will react with this glycogenin and forming a component like this, what we call glycogen primer. This is the first component. That means the glycogen primer, that means glycogenin cannot by itself directly react with the glucose units coming from UDP glucose. The first glucose we have to add to the hydroxyl group of tyrosine residues in glycogen. This is very important concept. Say this is glycogenin. How it ends? This is UDP glucose. We got it, and this UDP glucose, and it has to attach to the hydroxyl group. This is attached hydroxyl, then forming. This is the first glucose. That means it is called the initiation of glycogen primer. It is not exactly the full-fledged glycogen primer. Later, it by itself form 2 or 3 fragments. Then that becomes glycogen primer. Glycogen primer. This is very important step. The second important step. That means here the thing is, the glycogenin should get the first glucose from UDP glucose that forms. Later onwards, it adds 2-3 units, 2-3 individual glucose units that forms glycogen primer. And this is fundamental for glycogen synthesis. How? Then after we get it, it will be subject to glycogen synthesis. Here the most important gem is glycogen synthase. And for this here, the glycogen initiator synthase. So glycogen initiator synthase is for glycogen primer, and the glycogen synthase is for synthesis of glycogen. That means I told you already, glycogen synthase, it extends the glycogen in linear fashion. That means formation of alpha 1,4 glycosidic bonds, but not the branching pattern. The branching pattern will be done by glucosyl 4,6 transferase. So the thing is, the first glycogen synthase will add upon the glucose units. How? Say this is the UDP glucose. It will bring down the UDP glucose, then it will generate just the UDP. Then the glucose unit will come here. For example, say this is a component. Then we keep on add one by one by means of alpha 1,4 glycosidic bonds. We keep on add like this. Say this is the 13th glucose unit. For understanding, this is the UDP glucose 13th one, because they keep on adding 1, 2, 3, 4, 5, 6, and like that. Okay. For understanding, I'm just enumerating with respect to one particular example. And this glycogen synthase will bring the UDP and will attach the UDP glucose. That means the glucose from UDP glucose to the chain in a linear fashion, simply by forming alpha 1,4 glycosidic bond. Alpha 1,4 glycosidic bond. That's it. So it's like adding, just like we add the bricks, the glycogen synthase will take the glucose from UDP glucose and add by means of alpha 1,4 glycosidic bonds. But it's only in linear fashion. Then what we call branching. I told you, amylopectins, glycogen is an extensive tree-like structure. We want branches. How it ends? Say, then the issue, the most important enzyme, glucosyl alpha 4 to 6 transferase. This is a very important enzyme. The what we call branching enzyme. How it forms branches? Just imagine this is a glucose unit. It will break down. So this is the 10th one, and this is the 11th one, this 12th one, and so on. This glucosyl alpha 4,6 transferase, the name is transferase. It means it breaks down one alpha glycosidic bond. Say particularly here, it will break down, and it takes this smaller fragment and attach it to another glucose residue. Say how it ends. Say like this. It will attach to another glucose residue. Likewise, it will extend. Say how it attaches means by formation of alpha 1,6 glycosidic bond. This is very important. How it acts, the activity of this glucosyl alpha 4,6 transferase, how it transfers, it will break down a small fragment of some 5 to 8 glucose residues at one point, say here. Then it will attach to another glucose residues. How? By formation of alpha 1,6 glycosidic bond. Say break a alpha 1,4 glycosidic bond at one point and then transfer this small fragment to another glucose residue. That's it. This is an important enzyme because to get a tree-like structure, the activity of glucosyl alpha 4 to 6 transferase is essential. Whereas glucose synthase is just elongation. What we call elongation. Whereas the glucosyl alpha 4,6 transferase is branching point. So these together will form a full-fledged glucose structure. Like this. Ultimately, we'll get the glucose. The glycogen structure will be like this. For convenience, I'm drawing like that, just to avoid the wastage of time. This is how. This is the branching pattern. This is the branch, and this is a linear frame. Magnifying the same will be like this. This is a glycogen. Okay. So this is about the schematic representation of glycogenesis. Say the glucose will become glucose 6-phosphate by means of glucokinase, but glucokinase in liver, whereas hexokinase is present in muscle. It utilizes ATP, then glucose 6-phosphate become glucose 1-phosphate by phosphoglucometase, and glucose 1-phosphate become ADP glucose by means of catalyzing by the enzyme UDP glucose pyrophosphorylase. Then the glycogenin, what we call the glycogen primary formation, is essential by means of glycogen initiator synthase. How it forms? Say the tyrosine, the hydroxyl group of tyrosine residue of the glycogenin will bind with the first two glucose coming from the UDP glucose. Then late by itself it had 2 to 3 glucose residues forming glycogen primer. Then the glycogen synthase will act upon. How? Simply by adding the glucose residues in the way of alpha 1,4 glycosidic bonds in a linear pattern. Then what we call glycosyl alpha 4,6 transferase will form the branching pattern. That means formation of alpha 1,6 glycosidic bond that gives ultimately a tree-like appearance, a tree-like appearance of glycogen. This is about the glycogen synthesis. In all this process, 2 ATPs has been utilized. It's very important. This is one here. That means, in overall reaction, I am saying, say for every glucose residue we add in the for glycogen synthesis, there is a requirement of 2 ATPs. One here. That means one here, and another one is conversion of UDP to UTP. So it is with respect to energy calculation. We also study about this. One ATP from glucose to glucose 6-phosphate and another ATP from UDP to UDP. So 2 ATP totally for each glucose addition in glycogenesis. Okay. Then it's about glycogenesis. Then with respect to glycogenolysis, the same component but a